8th graders, today's lesson is 3.3 and 3.4 force in motion, and this will be the last amplify lesson we do for this unit. Our next little unit we're going to focus on is gravity, and that one is not an amplify unit, so we'll have a short little unit there where we learn a little bit about our weight versus our mass and how that plays into gravity. Okay. With that being said, before we begin with lesson 3.3 and 3.4, I want to review our last lesson, which was 3.1 and 3.2. So in that lesson, we introduced the concept of collisions and Newton's third law of motion, in that when two objects come into contact with each other, one object puts a force on the second object, and no matter the size or the mass or the speed or the movement of those objects, okay, that second object always puts an equal force back on the first object. Okay, so let's go ahead and take a look at what you guys did in this. One of your guys' activities was to do a simulation that showed you guys these collision forces. So in your sim tool, you guys went into 3.2, and you guys had two different options there. The first one, you guys looked at same mass collisions. So I'm just gonna look at one little example of that. So both of these pucks are the same mass. This one's obviously moving a lot faster. This one's stopped. So I'm gonna go ahead and hit run, watch them collide, and then I'm gonna hit analyze. Okay, when I reverse back to the point of that collision, I noticed that regardless of how fast A was going and the fact that B was stopped, each collision, this is the arrow that shows the force that A put on B, that was 100 newtons, and the force that B put back on A was also 100 newtons. And we know that B put a force on A even if it wasn't one doing the moving, because we had some kind of change in motion from A. So that means there must have been a force that acted on A. Okay, and those two forces again are equal, but notice that they are in opposite directions. Okay, if we went to different masses and looked at collisions between this puck here, which is moving fast, but also it's way heavier, okay, colliding with this at rest puck that's way lighter, we're going to see that same effect. So we're going to hit run and analyze, and we're going to go ahead and look at the point at which those two put a force on each other. Okay, we notice that the force of A, which was moving to the right, put a force in the direction to the right on B of 80 newtons. Okay, because we also saw a change in velocity on puck A, we know that B also put a force back on A, and what we see is it was in the opposite direction, but it was also 80 newtons. So even though A was way heavier and it was in motion, okay, and moving a lot faster than B was, they still put the exact same force on each other. Okay, so if you guys look at all these examples that we did, these were all the same mass, 100 newtons to the right, 100 newtons to the left, 140 to the right, 140 to the left, 60 to the right, 60 to the left. All of these are equal in strength, but opposite in direction. Okay, if we look at our different massed objects where A was way heavier than B, okay, 80 to the right, 80 to the left, 112 to the right, 112 to the, that should say left, and 48 to the right, 48 to the left. So even these ones, even though A was way heavier and in movement, whereas B was at rest, they still have the exact same strength. Okay, those strengths are equal but in opposite directions. Okay, your final thing that you guys should have done for your homework was to fix your model. And I just wanted to kind of talk about that. So I have the link pulled up here of your modeling tool. The only thing you guys needed to do in that modeling tool was show me the forces of this collision. So when those two come into contact, what does the force look like? Okay, what we know is that C was at rest, B was coming in to the right with a medium velocity. So that means when they collide, we're going to be looking at a medium strength force. Okay, we know that B is going to put a force on C when it hits it. Okay, it's going to be a medium sized force. But because B is going to change its velocity, we can see here it was moving to the right with a medium force. Now it's moving back to the left with a medium velocity. Okay, that means that C must have also put a force on B. And the key thing is that when we look back at our data tables, okay, all of these values are equal. So when we're talking about the strength of the forces or the size of those arrows, they should be equal as well, but in opposite directions. You guys can see them here. They're equal, but in opposite directions. Okay, so I'm going to go ahead and show two medium strength force arrows that are working in opposite directions on the other puck, but are equal in magnitude. Okay, so that's what your guys' model should have been, and I just wanted to go through that really quick. With that being said, let's go ahead and move on to 3.3 and 3.4. Your learning targets for today. I can describe the forces each object puts on the other in a collision, and then also how those objects might respond differently based on their mass. And that really is a good review of Newton's second law of motion that we learned about not too long ago. First thing you guys should do today is add key concept number 7 to your key concepts page. Even though the force exerted on each object in a collision is the same strength, if the objects have different masses, their changes in velocity will be different. So again, we learned just in that review from 3.1 and 3.2 that when two objects are in contact, they exert equal forces on each other, but in opposite directions, okay? That doesn't mean they'll respond the same, okay? Because they have different masses, and we know that mass plays into that with Newton's second law, they're going to respond differently. If I had a full shopping cart full of 30 frozen turkeys and my friend had an empty shopping cart and we stood 20 feet apart in the grocery store and pushed those at each other as hard as they can, okay, they're going to hit each other and they're going to exert the same strength force that you guys saw like with the little dynamic carts, but they're going to respond differently. My heavy cart probably is going to slow down, but it's still going to keep moving in the same direction. That empty grocery cart probably is going to turn around and change direction. Their change of velocity is due to the fact that they have different masses. And again, that's Newton's second law. Okay, your warm-up for today is to first make a prediction. In a collision, how do forces affect objects? I predict that. So you guys are going to circle either both objects should and will change velocity, only one object should change velocity, and then neither object should change velocity. Remember, any of our changes of velocity include those 5: speed down, speed up, slow down, start, stop, or change direction. So those are those 5 changes of velocity we've been talking about since the beginning. Okay, to test out your prediction you made in your warm-up, you guys will go to your sim link. You will go to the 3.3 warm-up, which is up here in the menu. And you guys will see the same setup that I just showed you in review for 3.1 and 3.2. Okay, we have 2 different size pucks. This one's moving 5 to the right. This one is at rest. Okay, you guys are going to go ahead and run your test collisions. Change the starting velocity of each object as described in the data table. Press run to observe the collision. Press analyze to determine the change in velocity. So this is very similar again to what you guys did in 3.1 and 3.2, except when you guys do this, you guys are going to change your velocity. The first one's set up for you guys, so you guys will have to change for trial or collision 2 and 3. Okay, you guys will run through that. And you guys will observe the change in velocity and analyze. So after they collide, click analyze, and you guys will see here's our change in velocity. So when A and B collided, A was going 5 centimeters per second, and then it slowed down to 3 centimeters per second. So that was a change of 2. That negative just means that it slowed down. Okay, it doesn't take any more force to slow down than it does to speed up. It doesn't take any more force for it to stop than it does to speed up or slow down. All of these forces are the same and cause the same similar effects based on mass. Okay, B on the other hand was much lighter. So we see that it was at rest and then it started moving and went 8 centimeters per second. So that was a change of 8 centimeters per second, which is a lot larger than the 2 slowing down. Okay, think about why that is. Okay, because you guys will come back to that. So you guys will tell me the change in velocity of A and the change of velocity in B. So you guys would have -2 for A, 8 for B. You guys will reset and build where this one's now moving 2 centimeters to the left. And then the third time you'll make the puck B move 2 centimeters to the right. Okay, the last thing you guys need to do is record the mass of A and B. So that can be found by comparing the colors. So you guys can kind of grab a new puck and build and be like, all right, A was 4 kilograms, what was B? Okay, so make sure you guys include that information as well. All right, then you guys will redo your prediction. Actual, in a collision, how do forces affect objects? I observed that both should and will change velocity. Only one object should change velocity, and then neither object changed velocity. So what did you guys see there? Okay, and then why? Why do you think the objects in each collision experienced a different change in velocity? Okay, once you guys are done with your warm-up, you guys will move on to activity 3, which is a little article. Last time when we did 3.1 and 3.2, you guys looked at the little survey question, which asked if a bug hits a windshield. Okay, what does that look like as far as the collision forces that they put on each other? So you guys will go ahead, take a second to read this article. Remember, our little trade-off that we have is that you don't have to read and annotate as long as you do a really good job reading. So please make sure you guys either listen really well or read really well or follow along as you listen, whatever, I don't care, as long as you guys do a good job reading. Answer these 2 questions as you read. What are the effects of the collision forces when objects with different masses collide? So again, you guys are looking at the effects. So what happens after the collision, okay, when different masses collide? So two objects of different size or mass, okay? And finally, what are the effects of the collision forces when objects of the same mass collide? Okay, so again, what's the aftermath of that? Okay, moving on, you guys have this little Sherman story where good old Bobby over here says, did you see that? When the ball crashed into the pins, those lightweight pins went flying, but the heavy ball barely changed its speed. So obviously we're talking bowling here. And poor Sherman comes in and says, yeah, the ball must have exerted a really strong force on the pins, but the pins didn't exert much force on the ball. Sorry, Sherman, but a pin exerts the same force on the ball that the ball exerts on a pin. It's a collision. Huh? Don't the forces have to be different to cause such different effects? Actually, Sherman, the forces in a collision are equal. The effects are different because, and of course you guys are going to finish that little guy's statement. How would you finish the explanation to Sherman? Why do colliding objects of unequal mass experience different effects? Okay, last but not least, you guys are going to move on to your final modeling quiz for this unit. You guys, again, will be graded on this as a quiz grade, so make sure you guys put some effort in, you pay attention, you do a good job, you check over your model before you submit it. Okay, what we learned is that our mass of our pod was 1,100 kilograms, which we found out was a little bit heavier than most pods. However, in comparison, our space station has a mass of 415,400 kilograms. So like a little bit bigger, okay? So with that being said, you guys are going to use that information to help you guys with the next modeling part, okay? First off, remember that the pod came in at a medium speed and the thrusters exerted a medium-sized force in the opposite direction, which in normal scenarios, this would have been enough to stop the pod and allow it to dock with the space station. But because our pod was a little bit heavier than normal, the pod didn't stop like it was supposed to. It did, however, slow down a little bit, so it went from like a medium speed to a slow speed. It did slow down to a small velocity, but eventually it collided with the space station. Okay, so what you guys are going to look at is what is that force like the second those two are colliding with each other? And then what do you guys think the response is going to be? What's going to happen to the velocity of those two objects afterwards? Okay, so the pod is moving faster than the space station. You guys have 3 claims. You guys are going to circle the claim you think describes the motion of the pod and space station after their collision. So claim 1 says the pod is moving faster than the space station. Okay, the pod and the space station are moving at the same speed, or the pod is moving more slowly than the space station. Okay, so those are your guys' options there. Again, you guys are going to kind of circle which one you think is correct. There we go. And then you guys are going to answer some questions on that. If the pod has a mass of 1,100 kilograms and the space station has a mass of 450,400 kilograms, what does the movement of the pod look like after its collision? Explain why. Tell me what you guys think that should be doing after it hits the space station. If the pod has a mass of 1,100 kilograms and the space station has a mass of 415,400 kilograms, what does the movement of the space station look like after its collision? So what do you guys think the space station is going to do? Remember, you guys are in space here, so it would be like similar to 2 bumper boats on the water, or that little video we watched the other day that showed that guy pushing the basketball away from him at the space station, okay, with no gravity. So explain why, okay? And then finally, this is your modeling tool. Okay, with that being said, you're going to use your predictions that you just made to do the modeling tool. So you'll right click and open this link here. Looks a little something like this. Okay, you guys only have 1 model to complete. So now we're just looking at what happens after each. And the really 3 claims just show us what you guys think is going to happen. Okay, so open the modeling tool. When you guys are done, you're actually going to screenshot it on the next slide. Your goal is to model the forces exerted when this pod and the space station collided. Show how the velocity of each object changed as a result of the collision. So really the 2 things I'm looking for is, can you guys correctly model the force in that during force box, the middle box? And can you guys correctly show me how you guys think the objects might be moving after they hit each other? Okay, show the locations of the pod and the space station during and after the collision. So if they're in the middle of a collision, where would you guys put those 2 pods, okay? If it's after the collision, where are those two objects going to be? Okay, show the strength of the forces exerted on each object during the collision. So you guys are going to use the arrows, the little pink arrows, to show how big the forces are and in which direction they are. And show the final velocities of the pod and the space station. Again, keep in mind which direction they're going to be moving and how fast they're going to be moving. The medium object represents the pod, and the large massed object represents the space station, which you guys should have that down by now. So let's take a look. Right here we have the space station is at rest. The little space pod is moving, and they have it moving at a medium velocity, okay? So if the pod hits the space station at the medium velocity, you guys are gonna drag a puck for the little pod, and you're gonna drag a puck. Remember that when you guys are looking at the during force, those two objects are going to be in contact, okay? We're looking at that exact moment that they're touching, that they're coming into collision with each other. Okay, after the force, you guys are gonna model where those two pucks would be, okay? So during the force, you guys are gonna use your pink arrows. Please do not, if you guys use more than one arrow, please do not stack them on top of each other or put them where I can't see the full arrow, okay? You guys can put them around the outside. Don't stack them on the pucks because I have a hard time seeing, so be mindful of that. And then you guys will use the velocity to show which direction and how fast you think those objects will be moving, okay? Think about if this is moving at a medium speed, what size of force is that going to give you, and how might that look afterwards, okay? Once you guys are done, you guys can screenshot your screen. You guys can paste it in on slide 16, okay? And again, that's going to be what I'm grading as far as your guys' test grade for this lesson. Once you guys are done with that, go ahead, fill out your wrap-up. Do you have any questions, yes or no? If you guys have any questions, type them there. If not, you guys can go ahead and circle 4, 3, 2, 1. How do you think you did? And once you're done with that, you are all done. I hope you guys have a great day, and I'll talk to you soon.